Hiya 12, this is video 5 of the photoelectric effect. We're carrying straight on from the previous video where we were talking about the interpreting the results of the photoelectric effect experiment and showing that the photon model can explain those results. So we were previously talking about, we derived this equation relating the kinetic energy of the most energetic electron to the photon energy and the work function of the metal. We're going to just carry on and see how we can relate this formula to the graph that we drew in one of the previous videos. So let's just rewrite that equation up here. And one of the results that we talked about was that if you change the frequency of the light, you can see the effect on the maximum kinetic energy, and the result looks something like this. And this was the threshold frequency, because below the threshold frequency we're not seeing any electrons being emitted. So if we compare this equation here to the equation of the straight line, EK max is what I'm plotting on the y-axis. F, the frequency, is what I'm plotting on the x-axis. So our first observation here is that the gradient of this line is equal to Planck's constant. So if you do this experiment, one of the things you can do is actually measure a value for Planck's constant. If we put in the constant value in our equation for a straight line, which remember is the value of the y-axis intercept, we can see that constant is equal to minus the work function. So if we extend this line down to where it would intercept the y-axis, we can put that value there of minus the work function. Okay, so remember this scale here is a scale of energy, and work function is an amount of energy. We could also think about if we rewrote this equation by substituting in h times the threshold frequency for the work function, and then factorizing it. Again, we get the fact that the gradient of the line is equal to Planck's constant, and looking at this, we also get the result that we've already put on here, that the x-axis intercept is the threshold frequency value. Okay, so that's kind of really one of the main parts about the photoelectric effect topic, that the fact that using the photon model we can in detail explain the dependence of the kinetic energy of the fastest emitted electron, that dependence on the frequency of the light that we're shining onto the metal. To finish off, there were two further observations. the third observation was that for a fixed frequency, the current, the electron current depends on the intensity. All right. Now, this one's a bit less obvious in terms of the wave model not being able to explain it. If we're using a fixed color, so fixed frequency of light, and we increase the intensity, so in other words, we make the light brighter, we are delivering more energy to the electrons in the metal. However, if you remember the graph of this result, we saw a directly proportional relationship. It's not clear that under the wave model, if you increase the intensity, increase the amount of energy you're delivering, it's not really clear that that energy should be shared out in such a way that we increase the number of electrons emitted in a directly proportional way. For example, why can't we suppose that that increased energy we're delivering goes to the same number of electrons, but just emits those electrons with a higher amount of energy? So the wave model doesn't really explain that observation in a quantitative way. The photon model, however, does, because if we think about our photons that are falling on our surface, remember we're talking about a fixed color of light here, and so that means that the energy of those photons is also fixed. So therefore, if we're increasing the intensity, if I want to double the intensity of this light, and I'm thinking about the photon model, each photon still has the same amount of energy, but what I must have done is increase the flux of the electrons. So if I double the intensity of the light, I'm doubling the number of electrons per second per unit area. If we call that the intensity, we label that as double the intensity. If I'm doubling the flux of photons, then I'm also going to double the number of electrons emitted. Okay, so remember, we're above the threshold frequency here. Each one of these photons is going to be absorbed by an electron, and we're going to get that electron emitted. So again, the photon model explains the dependency, the directly proportional relationship between the electron current and the intensity of the light. Finally, the fourth observation was that the emission is immediate. If we think about a light wave coming onto our metal surface, that wave is delivering a certain amount of energy per second to the area that it's shining on. Now, if we imagine that this was a low amplitude wave, so not a very bright light, in other words, that amount of energy being delivered per second we could imagine as being very low. We could imagine it being as low as we want to, down to a value of 0. We know that the electron that sat in that metal surface requires a certain amount of energy, the work function, to escape, at least. That's the minimum amount of energy that an electron is going to need to escape. So if the amount of energy delivered per second by the light is very small compared to the work function, then we should be able to set up an experiment where that electron is going to sit there for a long time before it gains enough energy, before it absorbs enough energy from the light wave in order to escape. So that's not what's observed in the experiment. The observation is you turn the light on and the electrons start coming out. With the photon model, we've got our photons coming into the surface. These photons are going to be absorbed and deliver all of their energy in one go. So you turn the light on, as soon as the photon reaches the surface, which of course is going to take a very, very short amount of time because they're traveling at the speed of light. As soon as that photon is absorbed by an electron, it instantaneously gains that energy that's required for it to escape from the surface. Okay, so 4 observations. All 4 of those observations can be explained by thinking about light as consisting of photons. The observations can't be explained by thinking about light behaving as a wave.